Hello viewers, welcome to another episode of All for E-Learning program. We shall take up the applications part of electric flux. Applications of electric flux. So let's have a small review. So I was telling you electric flux. Flux in Latin means flow. So it is flow actually, right? Flux actually is pertaining to vector field. Electric flux is linked to electric field vector, electric field. So this electric field, the interaction between two charges take place by the field, lines of force, right? Lines of force are imaginary lines along which the positive charge would tend to move like this. And this electric flux, I was telling you, flux is the measure of the number of lines of force passing through a particular space, whatever area of space you consider. It is the measure of number of lines of force, right? Then electric flux density we have defined. Electric flux density is nothing but electric field intensity, strength of the electric field, the characteristic property of the electric field. It is the measure of the strength, how strong the field is. Electric field exists, how strong it is, how much impact it can show on the charge. So that strength is electric flux density. So electric flux density is the electric flux per unit area. If I consider unit area, then the number of lines of force passing through that unit area, the measure of that is electric flux density. So we have taken the formula E is equal to phi by A, flux per unit area. So flux is EA, in fact it is E dot A, right? This is a vector, this is a vector, this is a scalar. It is the dot product of these both. So the flux phi is mod E mod A cos of the angle between them. So the flux is EA cos theta. This is the flux, right? So flux is the measure of number of lines of force. This is flux density into area. If I consider, now in this one, if I consider the flux, and even I was telling you, flux is a scalar. Even though it is a scalar, it can be positive, negative or zero. When is it positive? If the field lines, if the electric field lines and the area element and the electric field both are in same direction, parallel, theta is equal to 0, then the flux is E mod, actually flux is E dot A, right? So flux I can write as mod E mod A cos of the angle cos 0. So flux is simply EA, positive. Positive flux mean, right? Mathematically it is plus EA, but what does it mean actually? It means the flux is coming out of the surface. Whatever surface you have considered, the flux is emerging flux, and emerging flux, leaving flux. It is leaving the surface. It is leaving normally. Emerging flux, emitting flux. It is leaving the surface, leaving flux. Now that is considered as positive flux. Not only at this angle, for all angle theta lie between 0 and 90. 0 and 90. For all this, the flux phi is considered to be positive. Because for all this angle, cos 0, cos theta is positive. This is first quadrant of the plane, two-dimensional plane, first quadrant. For all these angles, cos theta is positive. Therefore, flux is positive. Then it is emerging flux or emitting flux. Now, if the angle theta, right? So, angle theta, if the electric field is like this, and the lines of force are falling on the surface like this, lines of force, the area element is normally away. So I was telling you, if I consider a area, surface area like this, then for this area, the area is a vector, the direction is normally away from the surface. Right? When you consider this surface, it is normally away A. When I consider this surface, it is normally away like this. So area vector is this side, but the electric field vector is in this direction. Both are in opposite direction. theta 180 degrees, then the flux is E dot A. So it's mod E mod A cos of 180. This is minus EA. It is negative flux. The flux is minus EA, negative flux. This is falling flux, incident flux. Right? The lines of force are falling on the surface. It is falling flux and incident flux. Now this flux phi, it is negative not only for this angle, for all the angles, theta ranging from 90 to 180. For all the angle theta 90 to 180. So that is the lines of force are like this and the area element is in this direction. So the electric field E this side, A this side, angle is theta, obtuse angle. This is for acute angle, it is positive. Right? This is for obtuse angle negative. For all theta greater than 90, then the flux is minus EA cos theta. Negative flux, falling flux, right? Incident flux it is. Second case. And the third and the most important, whenever, now this is to be understood carefully. Suppose if the field is like this and my surface area element is this way. If I consider area element like this, whose normal is in this direction, the angle between them is 90. If theta is 90, perpendicular, right, the surface is perpendicular, the surface is along the field, the area element is perpendicular theta, then the flux is, actual formula it is E dot A. So it is EA cos 90. We know cos 90 is 0. So therefore the flux is 0. What do you mean this? What do you mean regarding this aspect? It means whenever the line's electric field is in this direction and whenever the area of concentration, area of the plane, the area element what you consider is parallel, the plane of that area is parallel to the field. The plane, the lines of force are like this, the plane is parallel to it. In the sense the lines of force are going parallel to the surface. Now the area element will be normally away from the surface and the electric field is in this direction. Both are perpendicular 90 degrees. Now the flux is 0. What do you mean flux 0? Suppose had the angle been some angle like this, then the lines of force would have fallen on it. Incident. Had the angle been something theta, if the surface is like this, the lines of force are emerging. Now when the surface is parallel to the field, the lines of force neither fall on it nor emerge from it. Neither they are incident nor they are emitting out of it. Neither they are entering nor they are emitting. Now lines of force go parallel to the surface. Whenever the electric field is parallel to the plane of the surface, the flux is considered to be 0. Whenever the lines of force, whenever you consider the area element is such that the lines of force are going parallel to it, along it, over it like this, then there is no line of force neither falling on it nor emerging from it. No incident flux, no emerging flux. So the flux is termed as 0. 0 flux it is. Mathematically angle is 90 hence 0, right? But when you observe here, the lines of force neither fall on the surface nor they emerge from the surface. Neither they are incident nor they are emitting. Hence the flux is equal to 0, right? Let us understand these three things in a diagram. These three cases in one single diagram, right? A beautiful question was given based on this. Let us evaluate, let us understand this. Suppose that there is a uniform electric field E existing in a space like this. The lines of force are equidistant. This is electric field. Let me consider a cylindrical surface like this. A cylindrical surface. This cylinder consists of three surfaces. A circular area element here. A circular area element here. Let the area of the element is A. Let me name it as some Y. or y surface. Circular area element y or yes, y. Another circular area element here x, right? And this curved element, curved surface, that is z. Three surfaces. Now let me understand. First let us talk about y. The electric lines of force are passing like this. When I see from this side, this circular area element of y is in this form, and the area normal to it, if I take the area to be A and it is normally the direction of the area element is normally away from it like this. Normally away from it like this. The area is A and normally away. So if I consider this circular element, circular area, cylinder, suppose if I take a cylinder like this is the cylinder. In this cylinder, if I imagine, please see here, this circular area element. If it is a tin, for example, a cylindrical tin with a lid, imagine a lid over it. Then that lid, circular lid, right? Now that circular lid, that element, if I consider, now that circular area element has area A and its vector direction is represented like this. So here if I consider at this point here, E bar and A bar are parallel and in same direction, parallel and same direction. They are in same direction. So theta is equal to 0. So what is the flux through the surface y? Surface y. I have considered this as y. So surface y, flux through surface y, it is E dot A. So it is E mod A. Now both are in same direction, parallel. So cos 0. So it is simply EA cos 0 is plus 1. Answer is plus EA. The flux through Y is plus E. First point, very important one. Now next, let me consider the area element X. In the same cylindrical tin, in cylindrical box like this. Now if I consider this circular element, the base, let us say, initially this was the lid, here the base, the base of it. This one, even this is also circular. So when I look at the base, the surface is like this. When I look at the base, surface is this way. Its area element is outward normal. So its area element is outward normal. Both are of same area A, but away like this. But here the electric field lines of force are this way. They are incident. They are falling on it. So here A is. So at this point, if I find the flux, what is the flux through X? The area element flux. We know the formula flux phi is equal to E dot A. So it's mod A cos of the angle. Now here the angle, electric field is like this, area is like this. Both are in opposite direction. The angle theta is 180 degrees. They are anti-parallel, opposite direction. So it is cos of 180 degrees. So the flux through X, this circular element, and flux through X, this is mod E, that is just simply A, cos 180, that is minus 1. So the flux through X is equal to minus EA, right? Negative flux, because the lines of force are falling on that surface. Here the lines of force are emerging from the surface. This is emerging flux. But here the lines of force are falling on it. They are incident fluxes. Falling on it, entering flux. It is entering flux. Right? Yes. So first case, when theta 0, how would it be? If I take the area element like this, area, field, both are in parallel direction, both are in same direction, plus flux. Here, the circular part of that cylinder, area element is outward normal. This way it is. But the electric field is inside. Both are opposite, negative flux. Now let us understand, let us take up the flux through this curved surface. Now what do I mean the flux through the curved surface? So in this cylinder there are three surfaces. One is this circular part, that is X. We have found it as minus, because the electric lines of force are like this, they are falling on it. So it is minus EA. Now another circular part, this circular part is Y. So here the lines of force are outward. They are inward flux. This is outward flux coming out. So this is outward flux. You can even term it as outward flux. And here this is falling inside. This is inward flux. So here the lines of force are coming out of it. So here positive. So plus. Now how about the flux through this curved surface? This curved part. This part overall from here to there, total curved part. Now what is the flux? Now consider the electric lines of force. The electric lines of force are moving like this, parallel to the surface. At any point, if I take the, suppose let me take the area element here, Z, let the surface is named as Z. This curved surface is named Z. Let me take a small area element here. This small area element here has area like this. And on that area, the electric lines of force are like this. So E is in this direction, area element is normally away. The angle between them is 90 degrees angle. Now the flux here. Anywhere you consider, wherever you consider, if I consider the area element here, the area element is this side and the electric field angle is 90. So on this curved surface, at any point you consider, at any point, here the area is outward normal, here the area is like this, here the area is like this, here this way, it is this way. At any point it is outward and the lines of force is along the surface. The electric field is along the surface. At any point you consider, field is in this direction, field is along the chalk face, field is along the chalk face and the area element is normal. The angle is 180. Angle is 90, perpendicular. Here also the field, the electric lines of force are along the chalk face like this and the area element is normally away. So at any point on the curved surface, the angle is 90. Now theta is 90 degrees. Now what is the flux through the curved surface Z? Then we know the formula is E dot A. It's mod E mod A cos of the angle cos 90 degrees. So the flux through Z, the curved surface flux through Z, cos 90, it is 0. So 0 flux because the lines of force, electric lines of force are going parallel to the curved surface. Neither they are falling on it nor they are emerging from it. At any point on the curved surface they are parallel. So they neither enter into it nor they leave from it. So they are parallel. The flux is 0. So flux through the curved surface Z. This is the curved surface. Flux through curved surface. This is flux through the circular part. Circular part here and here it is circular part. This is curved. So the flux through the curved surface is 0. So first question, either he will ask you to find what is the flux through the circular part A, circular part Y emerging, this circular part Y, flux only due from Y, it is plus EA. What is the flux pertaining to the circular part X? Flux phi X is minus EA. And what is the flux pertaining to the curved surface? This curved surface flux phi Z is 0. Now the question he will be asking you to find what is the total flux through that cylinder, over this cylinder. The net flux through the cylinder. What is the total flux through the cylinder? Flux is a scalar, it's a scalar, we can just add algebraically. So the total flux through any surface is the sum of all the individual flux, the algebraic sum of all the individual flux there. So here there are three surfaces, flux along X plus flux along Y plus flux along Z. Flux being a scalar, the total flux will be the algebraic sum of all the flux, all the individual flux. So there are three surfaces X, Y and Z. So the net flux is flux along X plus flux along Y plus flux along Z. So therefore total flux through the complete cylinder is flux along X, we have derived it as minus EA. Flux along Y, we got it as plus EA. And flux along Z, Z is a curved part where the lines of force are parallel to the surface, net flux is 0. So the total flux through this cylinder is 0. A very beautiful question asked in previous entrance examination. Now, what do you understand from this? There is an electric field. In that electric field, if you place a cylinder in the electric field, there was an electric field like this E. In that I place a cylinder, then what is the total flux through the cylinder? The total flux through the cylinder is 0. Why 0? At one circular part, lines of force enter into it. Inward, they are going in, entering flux. From other circular part, lines of force are coming out, emerging. They are coming out of the surface. That is emerging flux. And this is a curved part where the lines of force are parallel to it. No flux neither enters into it nor comes out of it. So the total flux is 0. So we understand whenever there is a enclosed surface, enclosed volumetric surface, enclosed by from all sides, placed in a electric field, the net flux through that enclosure will be always 0. It need not be a cylinder itself. Suppose there is a non-uniform electric field like this, and in this one I place a enclosed volume like this, enclosed this way. Then at these points lines of force enter into this. Here they enter into the enclosure like this, and here they are parallel. And here they emerge out of it. So the total number of lines of force entering into the enclosure is equal to the number of lines of force emerging from it. The net flux over this will be 0. The total flux is equal to 0. So the net flux through the enclosure is 0. So whenever, a very good important point, remember, in an electric field, whether uniform or non-uniform, we are not bothered. Whatever be the nature of the field, when an enclosure, a volumetric enclosure is placed in it, then the net flux through it is 0. Because the lines of force enter from one side, they leave from the other side. The net flux is equal to 0. A very important thing to understand. The total flux through this enclosure, is 0. Very important point to remember. Okay, thank you.